Hi, I'm Jiale from Stanford University. Today I'm going to introduce our talk, Fair Grading Algorithms for Randomized Exam. This is a joint work with Jason from Northwestern University and Onno from Booking.com. In a traditional exam, the exam designer will prepare a question set and assign the same question set to all of those students. And one of the most commonly used grading rule, simple averaging, will grade the students according to the ratio of her correct answers. For example, if the student received 3 questions in the exam and get one of them correctly, simple averaging will grade her proportionally to 1/3. Nowadays, students are taking more and more online exams, and if we're still using traditional exam design, students might be easily communicating with each other. So, to deter cheating, one of the solutions is to design random questions to students. However, in this randomized exam setting, simple averaging seems to be unfair because it ignores the different question difficulties. For example, if those red questions are hard questions, blue questions are easy questions, the first student received 2 hard questions in this exam, while the second one received all easier ones. So simple averaging might underestimate the performance of the first student and overestimate the second one. And one of the main goals of our work is trying to come up with an algorithm that would give a more fair grade under this setting. Before getting into more details, here's an outline of the remaining talk. First, we're going to introduce the problem setting and give a formal definition of randomized exams. And then we're going to answer the question of how to measure the fairness of an algorithm. After that, we're going to show some simulation result before introducing our algorithm to give you a taste of how unfair simple averaging is, and also to show that it is possible to design an algorithm to improve fairness. In the last part, we were going to describe our algorithm and some theoretical result. One important question we're going to answer is how many questions do we need to ask to each student to give a fair grade to them? Now let's look at the problem setting. In a randomized exam, we're going to assign a small number of random questions to each student according to some task-assignment graph. This is an undirected bipartite where students are on the left, questions on the right, and each edge represents that corresponding student will receive corresponding question in this exam. We're going to generate the task assignment graph according to some family of random bipartites with 3 parameters. N is the number of students, M is the number of questions, and D is the length of the exam. So for each student, we're going to assign D uniformly random question to them. After that, we're going to grade the students according to the exam result, which can be represented by a exam result graph. This is a directed bipartite where any edge pointing from the student to the question represents a correct answer, and an opposite direction represents an incorrect answer. In practice, we can generate this exam result graph according to the student's answering sheet. And in theory or in simulation in our paper, we're going to generate it according to some model, which will be introduced with our algorithm later. Now we're going to answer the question of how to measure the fairness of an algorithm. To be clear, an algorithm can be an arbitrary mapping from the exam result graph to the grades. And the way we're going to measure its fairness is trying to compare it to some optimal grade, which is absolutely fair. And we call it a benchmark. The benchmark we choose is the expected grade of the student as if she is in a traditional exam. So imagine that we're going to assign all of those questions to the student and grade the student according to simple averaging. The expected that student have could be an accurate estimate of her performance over the entire question bank, which is fair among students. And we hope that the output of the algorithm will be close to the benchmark. But there are different ways to define this closeness. So in our question, there were 2 sources of randomness. So firstly, we're going to randomly assign questions to student. And student will also make random mistakes in the exam. And so correspondingly, there were 3 different ways to define this closeness. The first way is that imagine we're at a moment when students haven't received their questions, and we're going to calculate the expected grade that student would have over the random task assignment and over her random mistakes. After that, we're going to compare this expected grade to the benchmark. And this is what we call the X-ante bias. So intuitively, any reasonable grading rule would have a small X-ante bias because at this moment, we haven't assigned those questions and each student is facing the same situation. So there's no reason for the grading rule to treat student differently. So one of a more interesting case is for the ex-post bias, where we consider the moment where when students have already received their questions. So some of them might receive some easier ones and some of them might receive some harder ones. And we're going to calculate the student's expected grade over her random mistakes and then compare it to the benchmark. In the last case, we're going to compare the student's final grade to the benchmark. And this is what we call the ex-post error. So the ex-post error is the noisiest notion and the hardest notion to achieve when where X-ante bias is the easiest one. So these different definition of fairness notions share a similar intuition to the best of both worlds fairness in the literature of fair allocation. And similarly, we can easily come up with a grading rule to achieve X-ante fairness. For example, the X-ante bias of simple averaging is 0. However, students might be caring more about ex-post bias and ex-post error. And it turns out that simple averaging doesn't work well on those 2 notions. And also, it is possible to improve upon simple averaging. Here, we're going to show the simulation result. In this simulation, there are 35 students, and each of them is assigned 10 out of 22 questions. We're going to fix one task assignment graph. So some of them might receive easier exams, and some of them might receive harder ones. And we're going to see the student's expected grade over her random mistakes and compare to the benchmark. We denote the ex-post grade deviation as this difference, and the square of this ex-post grade deviation is exactly ex-post bias. And here's the result. On the left is simple averaging, on the right is our algorithm. So for simple averaging, so each interval here represents a student and is a confidence interval of the ex-post grade deviation. So for simple averaging, those intervals are everywhere. And you can see that some students who receive easier exams than others could achieve a positive grade deviation for up to 10%, while some unlucky student who receive harder questions in this exam might achieve a negative grade deviation for up to 15%, which means if we're going to use simple averaging in this randomized exam setting, in expectation, it will put the student into a run grade level. On the other hand, our algorithm tries to identify the question difficulties and adjust the grade according to it. So the grade deviation of our algorithm is much closer to 0. The second simulation is about ex-post error, which is the noisiest notion we have, and we will use bias variance decomposition to analyze it. So informally, the bias variance decomposition said that ex-post error can be divided into ex-post bias and the variance of the algorithm. In this simulation, it has a similar setting to the previous one, except that we're not going to fix the task assignment graph, but we're going to repeatedly generate random ones and take the expected ex-post error. The simulation result showed that our algorithm achieved a 8% smaller ex-post error, And after the decomposition, we can see that we actually achieve a 99% smaller exposed bias with 10% larger variance. And we want to argue that in practice, students will only take the exam once, so the variance of the algorithm inevitably contribute to the error. And instead of trying to reduce the variance, our algorithm focuses on how to accurately estimate the student's grade in expectation. So one takeaway of our algorithm is that it will reduce the exposed error by significantly reducing the exposed bias with a cost of slightly larger variance. Now we will describe our algorithm. Remember that we will use some model to generate the task assignment graph in theory and in simulation. And also, our algorithm is based on this model. This model is borrowed from Bradley and Terry in the literature of noisy comparison, and also Rush model in the literature of item response theory. This is a one-dimensional model with a parameter vector U, where UI for student I represents her ability, UJ for question J represents its difficulty. This parameter vector is unknown to the exam designer. We use a Bernoulli random variable Wij to represent the result of the answering process of the student. So Wij equals to 1 represents that student I will answer the question J correctly, and Wij equals to 0 represents an incorrect answer. Under this model, the probability distribution of Wij is the softmax of the student ability and the question difficulty. So specifically, the probability of Wij equals to 1 is the exponential of ui over the exponential of ui plus the exponential of uj, which can also be written as a function of ui minus uj, where this function is the sigmoid function. So our model is one of the item response theory models, and many item response theory models and related methods, algorithms are already used in standardized tests, including SAT and GRE, to generate score scales for alternative forms. However, we're in a different setting because those algorithms are used in a large scale, and we hope that we will find an algorithm that would also work well for a small exam. Now, our algorithm is based on the maximum likelihood estimators under this model. So Zermello and Ford have this theorem saying that the MLEs exist and are unique if and only if the exam result graph is strongly connected. Based on this theorem, we're going to show that when does the MLE exist and will be unique in our model, and also when it will be uniformly consistent. Here's some notation. N is the number of students, M is the number of questions, used parameter, U star is the MLE, and alpha is the maximum difference between the parameters, and D is the length of the exam. Our results said that the MLE under our model will exist and will be unique, and also will be uniformly consistent under some condition. Here we only present a simplified case when N equals to M and alpha is a constant. Under this case, as long as the exam length is much larger than log N, the MLE will exist and will be unique. And also, when the length of the exam will be at least log N to the power of 3, the MLE will be uniformly consistent. So assigning polylog number of questions to each student will be enough to give a fair grade to them. Our theory is an extension of Han et al., which focuses on Erdos linear graphs. In practice, however, the exam result graph is not guaranteed to be strongly connected, so our algorithm does something more. We give different predictions for different types of student question pair. The first one is the existing edge. So for those edges in the data, we predict the prediction we have is the same as the data. And for those student question pair lie in the same strongly connected component, from theory, we know that MLE exists, so we use this MLE for prediction. And for those student question lie in comparable components, we know that there is a directed path linking them. For example, the student in question linked by this black path. From the property of the directed graph, we know that any path linking those two vertices goes from the student to the question. So we regard this as a strong evidence that the student has a much higher ability than the question's difficulty. So we assign a probability of 1. If the path goes in the opposite direction, we will predict a probability 0. For the remaining case, the student and the question lie in incomparable components. And what we're going to do is that for this student, we're going to look at the first 3 types of predictions that we have already made for him, for her, and take the average of it as the new prediction. Now, if we compare our algorithm to simple averaging, our algorithm gives prediction on every student question pair, while simple averaging only gives prediction on the final grade. Also, our algorithm uses more structural information about the exam result graph. We analyze the MLE within the strongly connected component, and also we consider a different relationship between the components. But simple averaging only takes local information of the student, which is their in degrees and out degrees, representing their number of incorrect answers and correct answers. So intuitively, our algorithm will achieve a better ex-post fairness than simple averaging. And actually, we can bound the ex-post error of our algorithm by the square of the L infinity distance between the U star and U. Now, here's the extension and future direction of our work. It will be interesting to extend from the one-dimensional model to multi-dimensional model to incorporate different topics taught in class. And also, it will be important to provide a simple and clear explanation of our algorithm to students for practical use. This is a QR code for the archive version of our paper. And we have some other theoretical result beyond the simplified case. We also have some simulation, which would give you a reference on how to choose the right exam length, and also how our algorithm is going to reduce the exam length compared to simple averaging. Again, I'm Jiale from Stanford University, and this is my email. If you have any question or want to discuss about our problem, please email me. Thank you.